So in today's lecture, we've been looking at linearly independence, and we've been looking at the definition and doing some examples, kind of translating things back into homogeneous systems of linear equations. And we've been looking at special sets, small sets of vectors. Now, I just want to talk briefly about what is the geometry. Maybe this will help you reinforce some of the concepts. So in R2 and R3, two vectors being linearly dependent, well, that would mean that one is a scalar multiple of the other. But if two vectors are scalar multiples of each other, that means that geometrically, that means that they're on the same line. On the same line. So for example, let's say this is my first vector, v1, and here is, say, my second vector. It points in the other direction. And both of these vectors lie on this dotted line here. Oh, I forgot to label the second vector. So there's my vector v2, the green. So both of these vectors lie on the same line so that they're linearly dependent. What happens when they're linearly independent? Well, they will point in different directions. Okay, so here would say be my first vector, v1, and my second vector, v2. Okay, so then let me write that down so it's in your note. They point in the different directions. Point in different directions. So you can kind of see why the name linearly independent is being used. These guys are not linearly independent because they lie on the same line. Well, these guys are linearly independent because they don't lie on the same line. Now, as we kind of increase the our n space that we're working in, we get kind of different interpretations of what's happening. In R3, let's say you have three vectors. Well, what does it mean for three vectors to be linearly dependent? Well, they could be linearly dependent if all the same vectors lie in the same plane or in the same line. All in the same plane or same line. Right? The same line makes sense because you're just repeating what's happening in the case of R2. V1 and V2 point on the same line, and then maybe the R3 also points in the same direction. But maybe then the three vectors are all lie in the same plane, and then we would also say that it's linearly dependent. So V1, V2, V3 are linearly independent if no three vectors in the same plane. So whenever you have a vector, it defines one particular line. When I take another vector in R3, it gives me another in a different direction. Those two vectors combined describe a plane. Now, to be linearly independent, that means I would have to take a third vector that points outside of the plane. So the idea is every time you add a new vector, you're building up the space geometrically, you're building up the size of the space. Okay, so you have V1 defines a line. V2, if it's linearly independent, can't be in the line, so it has to describe a plane. The next vector can't be in that plane, so it has to go outside of the plane and describes an R3. So you can think about R4. What would happen is if you had four vectors. You have a first one line in R4, then you would have another vector, which would describe it, if it's linearly independent, which will give you a plane. If you take another vector which is linearly independent, it will point outside of that plane and giving you an R3. And then this is where it gets a little hard to visualize. Then you would have another vector, if it's linearly independent, pointing out of that R3 somewhere else into R4. So linear independence in some sense means that each time you add a new vector, you're building your space bigger and bigger. And in some ways, what the next result here is it's capturing this idea. But it's actually capturing it in the reverse way about capturing when it has linearly dependent. And what that says is instead of building your space, you actually get stuck back in the space that you built from the previous vectors. Right? So your theorem says if you suppose that you have more than two vectors, so what happens in that case? So you have a collection of vectors, and let's just assume that the first guy is in 0 to get us going. Then S is linearly dependent if and only if there exists some J such that the jth vector belongs in the span of v1 through vj minus 1. So kind of going back to what I was just mentioning in terms of the geometry, you start with your first vector. That kind of describes a line in Rn. You take a second vector. It either lies on that line or it points in a different direction and it gives you a plane. Then you take your next vector. Okay, if it lies in the plane, okay, then it's going to be linear dependent. So that's what that's capturing. If it lies in the plane from the previous two, then it's linear dependent. If it doesn't, then you can make your space bigger. Okay. Now I wanted to kind of quickly do a bit of this proof. I'm not going to do all of the proof, but I just want to make an observation. So we note that the statement has the form A if and only if B. All right. S is linear independent would be, or linearly dependent is the A statement. And if exists some j greater than 1 such that Vj is in the span, is the statement B. Right? So there's actually two things we need to prove. We need to show if A, then B, and if B, then A. Now, in the interest of time, I'm actually only going to show one direction. Okay, so we will show that if Vj is in the span of V1 through Vj minus 1, then S is linearly dependent. Okay, and geometrically, you should kind of keep in mind, say like you're taking V1, and let's say that V2 is in the span of V1, well, that would mean that V2 lies on the line described by V1. Okay. So here's the proof. If Vj is in the span, oh, forgot to put all the arrows here, V1 up to Vj minus 1, then Vj is a linear combination. C1 times the first vector plus C2 times the second vector up to Vj minus 1. Oh, forgot the coefficient. Put that in. Cj minus 1, Vj minus 1. All right. For some not equal to 0. For some C1 up to Cj minus 1, not all equal to 0. Okay. But that means if we rearrange this equation, but then the 0 vector satisfies C1 times V1 plus C2 times V2 up to Cj minus 1, Vj minus 1 plus minus 1 Vj, and now I can throw in a bunch of extra values of 0. 0 times Vj plus 1 up to 0 times Vp. And what we have here is we've written 0 as a combination of my vectors v1 through vp. The coefficient of this particular vector is minus 1, so we have a non-trivial solution. A non-trivial solution, so the vectors linearly dependent. Okay, so there we go. We have a theorem that kind of tells us one way to test whether your set of vectors is linearly dependent, and you're basically doing one vector at a time. You take your first vector, you look at the span, and then you say, oh, is then my second vector in the span? If it is, then it's linearly dependent. If not, my set is still linearly independent, and I add it to my set. Then I look at the third vector. Is it in the set? If yes, it's linearly dependent. If no, it's independent, and I carry on. So in the last part, I'll just look briefly at kind of another condition where we can tell immediately that our set of vectors is linearly dependent, and we'll look at some kind of cautionary examples to keep in mind when you're looking at linearly independence and dependence.